thank you everyone for coming. It smells really good in here, so thank you for bringing your lunch. Yeah, so today I'm going to talk about how much versus what kind. So thinking about PM2.5 from those two perspectives, right? So part of the health effect is from how much stuff is in the air, and part of it is from the kind of stuff that's in the air. And been thinking a lot about what that means in terms of trying to make sure our epi studies line up with what we actually regulate. And you'll see that I think we need to start paying a lot more attention to the actual composition of the particles. Before we get started, how many are you epidemiology students, occupational health students?
Occupational hygiene.
Occupational hygiene. So mostly on the exposure side and not so much on the epi side. Okay, so if you have any questions about any epi stuff, just speak up and I'll be happy to answer. So I was looking for a quote to kind of like motivate the theme of this talk, and I found this one from Mark Twain. It says, "It ain't what you know that gets you into trouble, it's what you know for sure that just isn't so." Okay? And so this theme kind of runs across the top. So what's our regulatory definition of PM2.5? What's really the target exposure, right? So the US EPA describes PM2.5 as fine inhalable particles with diameters that are generally 2.5 micrometers and smaller. Everyone knows that. Other agencies have the same definition. The kind of particles is not mentioned at all, right? So it's just how much stuff of a certain size is in the air. That's the underlying exposure that we want to estimate the health risks for. So the really how much effect is the only metric of regulatory concern, okay? Now this raises an interesting question in that to align with the regulatory definition of PM2.5, our epidemiological studies need to be estimating the health impacts only of how much PM2.5 is in the air, independent of composition, right? Because that's how we define PM2.5 as a regulatory metric. Doesn't say we have a standard for this kind of PM and a standard for this other kind of PM. We have one standard for all PM, right? So we want to be estimating the health effects of how much stuff is in the air, independent of composition. So how often do we actually do that? When we do studies of PM2.5, say in mortality, how do we do those studies generally? No one's read any of Mike's work? None of Sarah's work? Take a guess. How do we do it? I know you probably have a intuitive sense. Doesn't need to be specific and scientific, but just how might you go about in all this cohort work that we do, the work that informs all the regulations? How are those studies done? Okay, so what we do is we compare the survival experience among people who live in a lower exposed area to a higher exposed area, right? So we have all these fancy methods using satellites and chemical transport models where we can assign exposures to the whole country, and then we can follow people over time and see that if people that live in areas with higher PM2.5 have higher risks of mortality or lung cancer mortality than people that live in lower areas. Now, those exposure measures that we use, typically we don't have information on composition, or we have it but don't use it, right? Usually we're just getting a mass concentration, how much stuff is in the air of a certain size, and we compare health risks across that gradient. So it's a bit of a problem because in sort of causal inference literature, in order to estimate the real causal relationship between an exposure and an outcome, we need to assume that there aren't multiple versions of the same treatment that can give rise to different outcomes. Am I muted, really?
No, it's okay.
No.
Okay. Okay. So what does that mean? So imagine you were looking at the effect of a new drug, but there were multiple versions of that same drug, right? You would need to consider that in trying to estimate the health effect of the drug, because those different versions of the drug could give rise to different health effects, right? So when we do studies of PM2.5, what we're really assuming is that all of that mass is the same. There aren't multiple versions of it, okay? And so in using this language of version of treatment, when we do these studies, traditionally, the total mass concentration is the treatment, okay? How much stuff is in the air? That's the exposure, the treatment we're interested in. And the chemical composition is the version of treatment, right? So the different ways of adding up the components in PM2.5 determines the version of treatment that you get. Problem is that there's almost always multiple versions of treatment for PM2.5. There's literally an infinite number of ways to add up all the different components to arrive at the same mass concentration. You can get 10 micrograms per cubic meter by all kinds of different combinations of sulfate and nitrate and black carbon, organic carbon, transition metals, right? So there's always multiple versions of treatment. And we know that some of these toxicants they're known toxicants, things like arsenic, right? Lead. Some are harmless, like sea salt, for instance, right? And PM2.5, this magic thing happens where if we had the components of PM2.5 in pills in our hands, they are treated much differently from a regulatory perspective. If we have arsenic and sea salt, we treat those a lot differently. If you throw them in the air, they magically become PM2.5 and we treat them exactly the same. So, okay, so this is called the no multiple versions of treatment assumption or the consistency assumption. And again, this means that we assume that all versions of PM2.5 are the same regardless of composition. Okay? Put another way, it means that we assume that two interventions, so two regulations that reduce PM2.5 by some amount, are going to have the same health benefits regardless of how we achieve that reduction, right? So if we target coal combustion or sea salt, we assume that that's going to have the same exact effect. That's what we do, okay? And this causes a lot of problems if we want to estimate the health risks that are only attributable to how much PM2.5 is in the air, okay? And again, that is what we're interested in based on how we define it from a regulatory perspective, right? That's the estimate that we want. We want the health effect of how much mass is in the air independent of composition. And so why does this cause problems? So this is a DAG. Have you guys heard of DAGs before? And how you can use these sort of causal diagrams to lay out your assumptions when you're doing analysis? So we use these a lot in epidemiology just to make it clear to readers why we adjusted for things we did. It's also very useful just as a researcher to make sure that how you're framing the problem makes sense. Okay, so typically we have our outdoor PM2.5 concentration, right? That has some impact on personal exposure to PM, which contributes to something bad, mortality, cancer. And then we have things that are confounders. So these are things that are independently associated with the outcome and also associated with PM2.5. So this could be, say, neighborhood level SES, for example. Now, the problem with PM2.5 is that you also have multiple versions of treatment, okay? So there's many different ways to add up all the components to achieve a mass concentration. Now, the real problem arises when you have components that are independently associated with the outcome, because the components are by definition related to the version of treatment, right? Because the components are what makes the version of treatment. Okay, so if you have components of PM2.5, say, lead or PAHs for lung cancer, that are also independently associated with the outcome, you're going to get a biased estimate of the total PM2.5 because of this, what we call a biasing path through here. So you need to consider components that are a cause of the outcome if you really want to get a true estimate of the health effects of how much stuff is in the air. Okay? And so, just said that. If you don't do this, the estimate that you get for total PM2.5 is some unknown combination of how much stuff is in the air and the kind of stuff. And you have no idea which one is driving it. Right? You just know that we've mixed the two together. This is confounding. Right? This is how confounding works. And this is present in basically every study we've ever done for total PM2.5. Certainly all the ones that have been used for regulation, all the famous ones. Okay? And so as part of a study that Mike Light and I was a part of, we recently published a paper in environmental epidemiology trying to see what exactly this means in terms of bias in the effect for total outdoor PM2.5 when you take the different components into consideration.
Scott, can I just jump in?
Yeah.
Just I want to ask you a question maybe to help
Yeah.
others understand. Would you have the same problem if you thought about an occupational exposure where all you had was like job and there were multiple chemical or physical exposures in that job? So if you said like,
Yeah.
you know, cancer mortality risk for woodworking, and you actually didn't, would you have the same problem?
Yeah,
And I don't know
if you used.
Can you repeat that?
So the question was, would you have the same problem if you were looking at, say, job classification or job type? So I think yes, if you were using like a job category as the exposure, then you could imagine that, you know, people that are, say, firemen, not all firemen are going to have, like, fireman doesn't mean the same thing for everyone, right? Like, are you a fireman in a city? Are you a fireman in a small town? Are you fighting forest fires, right? So that what firemen mean, what that treatment means, in this case, treatment is just your job title, but that's going to represent something different for everyone. Does that make sense? Okay. So how did we do this study? So when we do a lot of our air pollution cohort work, has anyone ever gotten the long form census in the mail? Fill out? Yeah, does everyone know the CanCheck cohort? So our national census in Canada has been linked to mortality records, cancer incidents, and tax records. And so we have this great population-based study that we can link environmental exposures to look at mortality and cancer incidents. So in this study, we followed 3 million people across Canada from 2016 to 2019. And we had sort of 3 main exposures that we looked at. One is the total PM2.5, which is what we normally look at, estimated using our satellite models with chemical transport models. So this gives us an estimate of total PM2.5 on about a 1 kilometer resolution. And then we also have estimates of 2 specific components of PM2.5, the sulfate and the nitrate concentration. And the reason that we picked sulfate and nitrate is because the model predictions for those components are really good. They match up really well with ground level measurements. And there's also existing studies showing that these components are independently associated with mortality. So independent of the total mass, there are studies showing that these 2 components are independently related to the outcome we're interested in. So the main question here is that what is the relationship between total outdoor PM2.5, so how much mass is present, when you take into account the kind of mass that's present, right? Because remember that if we don't do that, we're mixing up the combination of the 2, right? What we'd like to do is get the health risk just related to how much is in the air, irrespective of the kind that's there, okay? And so the way we did that was through 3 main analyses. First, we did what we would normally do is just look at the total PM2.5 mass. That's what we've done, that's what most people do. Next, we looked at total PM2.5, but we also adjusted for how much sulfate and how much nitrate was actually in the PM2.5. Okay, so we're accounting for the kind of PM2.5. And then we did essentially the same thing, but in a slightly different way. So what we did is we did a linear regression model where the outcome is PM2.5 and the predictors are sulfate and nitrate. And then the residuals of that model is basically variation in the total mass that's not explained by those 2 components. It's essentially the same thing as this, but the reviewers wanted us to do that as well, so we did it. So is everyone clear on what we're doing here? All right, so we do what we always do, just looking at only the mass, and then we try and estimate the mass effect, accounting for the kind of mass that's present. Okay. And so here's a DAG describing what this would look like. It's basically the same model kind of DAG that I showed you, but for our specific example. Okay, so our exposure of interest is this total mass concentration, so how much stuff is in the air. And then we adjust here for sulfate, because sulfate is, of course, a cause of diversion of treatment and is also related to mortality. And then we adjust for other confounding variables like SES variables that are possible confounders in this relationship. We good?
So so that kind of arrow in the far upper right there, there's already some actual like numerical estimate of how much sulfate alone would contribute to that mortality?
So
Like there's some quantitative link there?
yeah, so there are studies that have looked at like the effect of sulfate on mortality, say across the US, and they see an effect of sulfate on mortality even after you adjust for like just how much stuff is there, right? So the definition of a confounder is something that's independently associated with the outcome and also associated with the exposure you're interested in, right? So we adjust for that for the same reasons that we would adjust for area level SES.
I was just wondering if the adjustment is like a quantitative thing rather than like a, I don't know, like a relation where you just say this may be correlated. You're actually
No, we're actually have a,
this correlated.
oh, well, we have continuous, the same way we have a measurement for outdoor PM2.5 that we have in our model.
Oh, you have the remote sensing. Like
We have a quantitative measure of sulfate that's in the model.
Is the sulfate in mass concentration as well, or like a fraction, or how is that expressed?
It's a mass concentration as well. We've done it both ways. But in this case, it's a mass concentration. It's easier to understand on the graph.
So have you done metals in here, that sort of thing as well?
Not in this study because we don't have remote sensing estimates for it, but I'll get into why. The reason I think that actually sulfate is important is that it's not so much the sulfate itself, it's that the sulfate actually makes the particles more acidic, which makes the metals more biologically available.
Mm-hmm.
And so I have a slide later on showing how we've actually tested that, but that's why I think sulfate is important, is because the metals themselves don't contribute that much to the total mass of PM because they're measured in like nanograms per cubic meter.
Depends where you are.
Yeah, I mean, at least in the ambient air, it's not, I mean, because sulfate, I'll show you later, but like it could be 40% of the mass is sulfate. It's never going to be 40% of the mass of metals unless you're on a railway or something, or like
Or if you're in trail.
yeah, maybe in trail it's higher, but even then I've done studies in trail. I don't think it was 40%.
Okay.
It's I mean, there are places I know that in Courtney when we were doing our wood smoke work there, a ridiculous proportion of the mass was just the glucose sand, the marker of biomass burning, just because it's like the only source in the wintertime. All that to say, does everyone understand what's going on here in terms of the analysis? Okay. So what does this mean? So this is just showing how much variation there is in these two components of PM2.5, getting at the idea of this multiple versions of treatment. Okay. So across Canada, for places that have a concentration of about 10, there are places that have 4% sulfate. There are places that have 25% sulfate, right? Not the same treatment at all, right? Very similar thing for nitrate and sulfate, right? So you see that the composition varies not only across levels of total mass, but even within, right? So that means across Canada, people with exactly the same mass concentration can have vastly different actual treatment values, right? So if you're doing contrast and health risks across a gradient of PM2.5, and you get some risk for total PM, is that a mass effect or is that a composition effect? If you don't include the composition, you have no way of knowing. You just know it's some combination of the two.
And Scott,
Yeah.
isn't this also important, like even if, let's say, nitrate or sulfate were not toxic?
If they weren't toxic, there would be no reason to adjust for them.
Except that it still shows there's other things, like composition still differs in ways that you don't know, right? So if you have like 100% mass,
Yeah.
and 40% of it's sulfate, even if sulfate's not toxic, that 60% is going to be made up of different things that you don't know about. Like I would think this still matters even if these are not toxic.
It matters most if they're independently associated with the outcome, because that's what you're trying to avoid. Otherwise, you don't want to be mixing up the effects of the kind with the how much, right? So you still have to know something about the toxicity. We don't know everything about the toxicity of PM. There's lots of components. We don't know everything about which are the most important, but we certainly know for sure some are more important than others, right? And so this is the kind of point that I'm trying to drive home. And so here's what we get. Okay, so this is for non-accidental mortality. If you look at just the total PM2.5, you get about a 6% increased risk per interquartile range. This is what we always see. Now, if you look at the total mass effect after you adjust for the kind of mass, there is no total mass effect. The effect is driven by the kind. not the how much. So you see an effect for sulfate, you see a smaller effect for nitrate, right? And so this total effect is not driven by how much is there, it's driven by the kind of mass that's there. Okay, and you see the same thing for cardiovascular, and you see the same thing for respiratory. Okay, you don't think about the composition, you see an effect of just how much stuff is there. When you account for the kind of stuff that's there, the risk is really attributed to the kind of stuff. It's not how much is there. Okay, and the neat thing is that for lung cancer, you actually see the opposite, because lung cancer, sulfate and nitrate were actually inversely related with lung cancer risk. So in this case, the confounding goes the other way. You underestimate the risk for lung cancer when you don't adjust for this composition differences. Right? Confounding can go either way, right? You can overestimate or underestimate depending on relationships between the variables. So in this case, our estimates are too high for total PM2.5 when we're looking at, say, cardiovascular and respiratory mortality, and they're too low for lung cancer. And here are concentration response curves that we like to plot. So you see that for sulfate, basically, I mean, linear-ish, right? So there's a bit of a leveling off here, but pretty much increases across the concentration spectrum. So this kind of PM mass is having an effect, but the total amount of stuff, not really, right? When you account for the kind of stuff that's there, the effect for how much is there really goes away. And turns out we're not the only ones to sort of note this. This was a study that was done in the US among 15 million people. And these plots are showing kind of what I just showed you. So this is the effect of total PM, right? So you see increases for all cause, cardiovascular and respiratory. And this is the effect for total mass when you remove these different components, okay? And so what they see is like when you remove the sulfate, again, the effect for total mass goes away. Okay. There's also, they have nitrate here, it goes down for respiratory and goes down a little bit for all cause, but not as much as it did for us. But just driving home the fact that when you incorporate this information on the kind of PM that's present, you get a much different answer for the total mass, right? And again, the total mass that's the estimate we need. That's what we regulate, right? By definition, we need a health risk for how much stuff is in the air because that's the metric we chose. So this is our study that we did across Canada where we looked at combinations of both metals and sulfate. And this gets to your earlier question. And so basically this analysis is showing health risks of short-term variations in PM2.5 and risk of heart attacks. And what we saw, we were able in this study to look at if you were exposed to, say, low metals and low sulfur, or high metals and high sulfur. And what we see is that even if you're exposed to, say, a high level of metals, you still don't see a risk when the sulfur level is lower. But when you have high metals and high sulfur, then you start to see the risk, right? So it looks like the sulfate is really just making those metals more available, okay? And so if you have low metals and then you increase the sulfate level, you see a little bit of an increase, but certainly much different than when you have high metals, okay? So again, this kind of PM is really mattering in terms of the health risks that you're seeing. And too bad Sarah left, but this is actually from our students project. Again, just highlighting how maybe the author is actually in the room. I'm not sure. So this was the study looking at wildfire smoke, wildfire PM2.5 prenatal exposures and ear infections and lung infections. But I wanted to highlight again, they did the analysis separately, looking at PM during the extreme wildfire seasons and then sort of below average wildfire seasons. And for the same increment of exposure, they see pretty strong association during the strong wildfire seasons and an inverse relationship during the regular seasons, right? So the total effect or the effect of that total mass is a lot different, right? It's not even different. It's not just different in magnitude, it's different in direction, okay? So there's lots of examples of how incorporating this information on the kind of PM is relevant to health. So my main argument is this. So risk estimates from our existing studies of total PM2.5 typically reflect some unknown combination of how much PM is present and the kind of PM that's present, right? That's all we know. We don't know what the relative contributions are, but it's some mix of those two things. When we do that, traditionally, we then attribute the entire effect just to how much is there. So we just assume, oh, we did a study of PM2.5, we saw risk, it must be explained entirely by how much is there. Okay, that's wrong. It's absolutely wrong. And so in reality, we actually don't have very many studies that estimate only the how much effect. And that's the effect we actually need so that it lines up with what we regulate, right? Because traditionally what we estimate is some unknown combination of those two things. And so for this reason, the risk estimates that we get, they don't really align with how we actually define and regulate PM2.5. And so this also has implications for the really consistent heterogeneity that we see between studies around the world. So this is a study that was done by Mike and others that were looking at the sort of shapes of concentration response curves for PM2.5 around the world. You can see they're different, right? So there could be a number of reasons for this. There could be population differences, et cetera, but certainly, if the kinds of PM vary so much across Canada, even within a given concentration, there's a lot of differences across countries, right? So we see a lot of variations in these shapes of concentration response curves. This is a paper from Nature that had a whole article on sort of how we should be thinking about toxicity of PM and how we should be ranking sources of PM2.5 depending on how harmful they are. And they show this plot, which is basically on the x-axis, the total mass concentration, and then the PM2.5 related deaths, right? And so you can see that for a given mass concentration, say 20 or 10, there's a lot of variation in the mortality that's attributed to exactly the same concentration, right? Again, multiple versions of treatment. These mass concentrations mean something different in these different places. So I do want to highlight that this does not mean that outdoor PM2.5 isn't bad for us. It absolutely is, okay? But it's not all created equal. And if we pay more attention to these compositional differences, we can be a lot more efficient in terms of targeting interventions to improve population health, right? Because if you know the kind of PM2.5 to target, you can do that. Instead of trying to take the whole country's levels down by a certain amount, you target the most important sources, you're likely going to get the same health benefits for a much lower cost. And if we want to do this, though, we have to start thinking separately about this sort of how much effect versus the what kind of effect. Okay, so what are our options? So one option is just to do nothing. We just keep doing what we're doing. The cost of that, however, is that we're never really going to get at the true estimate of that how much effect, which is what we need to know in terms of regulation. And we also shouldn't expect homogeneous benefits from any policies that are implemented based on these estimates, right? Because the kind of PM varies across the country, right? See, if we don't have an estimate that also incorporates the kind of PM, just reducing mass isn't going to have the same effect everywhere because it's not the same kind of PM everywhere, okay? Now that's what we do now, but we shouldn't really expect that those benefits are homogeneous. Now, what I think we should be doing is focusing more on the components, especially components that we know are independently related to the outcome and could be confounders of this version of treatment outcome relationships, right? So we need to be looking at the health effects of how much PM is present across levels of similar composition, right? That's really what we want to know. And this will improve the validity of our estimates that we base our regulations on, which is this sort of how much effect that I talk about, and also help us identifying sources and components that we can target for future regulations. So with that, I just want to finish again with this quote, that it isn't what we don't know that gets us into trouble, it's what we know for sure that just isn't so. And I really think that applies to what we've been doing in air pollution epidemiology around PM, and there's probably a lot of work for us to do to try and make these studies a bit better. So that's it, thank you so much.